Recurrent neural network. This is one of the state-of-the-art deep learning method. What is so special about it? It has an internal memory and it can remember important things from the input and the previous layers. Because of this internal memory is especially good for language models and time series models. Let's look at an example on how it is good for a language model. Just imagine sky is ... So we need to predict what comes next. Now, if we only have is, the previous word from the blank, can we actually predict what comes next? But if we have sky is, then it is probably easy for us to think that it can be sky is blue. Let's check in the Google search bar. So if I type is, it brings all kinds of stuff, right? Now, if I type sky is, the first thing is sky is blue. So it gives something that is more intuitive for it, right? A little bit of short-term memory helps with the prediction of the next word. For the time series models as well, we need to look at a sequence, not only the previous layer. This was the very brief short overview. Let's dive into the model. For this exercise, we are going to use IMDb reviews dataset, and you can simply load it using tfts.load method. And it has its training and testing portion separately. You see the samples of the data. It has this text data, movie reviews, and then the class. There are two classes, 0 and 1. You see some are 1 and some are zeros. 1 and 0 represent positive reviews and negative reviews. This text portion is our features, and 1 or 0, these are our labels. If you look at it, these are all tuples. The first element is a sentence review, and the second element is the label. We are looping through each element and separating the text portion, the reviews, and the labels. So training sentences, training labels, testing sentences, and testing labels. And here we are converting the labels to arrays. After we separate the sentences and labels, how the sentences look like, here you see we have a list of sentences or reviews only. So here I'm showing you only first 5, and these training sentences, these are going to be our training features, as you already know. When we have text data, we need to do some kind of data processing so that they become numeric values and we can use them for our modeling. The next steps are going to be the processes how we convert this text data into numeric form. So these are some variables, vocab size 10,000. That means we are going to allow 10,000 vocabulary, 10,000 unique words. Embedding dimension 16, each word will be represented as a 16-element vector. Max length 120, each sentence should be no more than 120 character long. You know, we need uniform size data. Each row has to be the same size, right? In the trunk type post, that means if we have a sentence longer than 120 words, we are going to chop up the extra words. And OOV token is just an empty string like this. If we have any unknown words, see, we are allowing 10,000 vocabulary, 10,000 unique words. If we have more than 10,000 words and we have unknown word, that will be represented as this. What if our sentences are less than 120 words? That sentence will be padded with zeros. So each and every sentence will be the same size. Here we are importing tokenizer and pad sequences. So the tokenizer, it takes number of words. So the number of words we want, so we have vocab size 10,000. So now words will be 10,000 and OOV token. And I already explained what that is. So tokenizer.fit on text. We first transform the training sentences and tokenizer.word index. And if you use tokenizer.word index, you get this. So you saw each word got a number. Okay, we got a number for each of the word we have in our training data. Tokenizer.text to sequences. We have the words in our training sentences. So this text to sequences function is going to replace each word with its corresponding numbers. So each training sentences will be sequence of numbers. And then padded, then pad sequences. That means we already gave 120 the maximum length, and we are giving the sequences, the number sequences for each training sentence. So this path sequences function will make each and every sentence an uniform length of 120 characters. Because we have numbers now, 120 numbers long. And as we mentioned, if it has more than 120, it's going to chop off the extra, and if it has less than 120, it will be padded by zeros. We do the same with testing sentences as well. Well, our data is ready. Now, model development. So here we are developing a model, tf.keras.sequential. It's going to be a sequential model. The first layer is an embedding layer. Embedding layer, it takes the vocab size. We have 10,000 and the embedding dimension 16. So this embedding layer is the layer where each word gets represented by a 16 elements long vectors. And you can see the 16 element because we mentioned embedding dimension as 16. You can make it 32, 64, whatever you want. This is a hyperparameter. You can play with it. And here we have a simple RNN layer where I'm using 120 as input. This is also another hyperparameter. You can play with it. The next, we go to our regular dense layers. I'm using 2 dense layers here. You don't have to use 2. You can use only 1 if you want, the final one. But I'm using 2. The first one has 100 neurons and activation value. And the second one, I have 1 because we have only 2 classes and activation sigmoid. So this is the model. In the hyperparameters, we have the vocab size. I used 10,000. Feel free to use less or more and see what happens. Embedding dimension, this is also another hyperparameter. I used 16. Feel free to play with it as well. SimpleRNN, this input 128. The number of neurons, 100. You can change it. Then activation function RENU. Feel free to use different ones like TANH or LickRLU, CELU, or anything else. The model development is done. After that, it's simply you compile it. I use binary cross entropy as loss function, optimizer atom, and matrix accuracy. I trained it for 20 epochs, and then model.fit. You use the training data. After you finish sequencing and padding, that becomes your training data, training features. This one, the training labels final. As you remember, I used training labels final here where I just converted the training labels list to a NumPy array. And then epochs, num epochs that I already defined here, 20. Invalidation data, testing padded, testing labels final. You see testing padded here when we just sequence and pad the testing sentences. And then testing labels final. After 20 epochs, what we have accuracy 85.72 on training data and 73.19 on validation data. You can see some overfitting there. So I already mentioned what are your hyperparameters. So this is up to you. Please feel free to tweak these hyperparameters and see if you can improve this overfitting situation. But I should warn you that usually in natural language processing problems, you will always see some overfitting. Some overfitting is always normal because you need to understand no matter how many words you train on, you will still find new data in your test or validation set. So in natural language processing problems, some overfitting is actually acceptable. Alright, that's all I wanted to share with you today. Please like, comment, share, and subscribe if you like this video. Thank you so much for watching.